Welcome to the third session of this circular function series. In this session, we will review supplementary and complementary relations, compound angle formula, especially the double angle formula. We will solve inverse trigonometry function related problems and demonstrate how to find angles in its general form through 12 worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the third session of this circular function series. Here, example 1 is to find the value of secant x given that tangent x equals 2 over 5 and x is in the third quadrant. Since tangent x equals 2 over 5 and x is in the third quadrant, secant x equals negative square root of tangent squared x plus 1, which equals negative 29 over 5 after being simplified. In example 2, it is given that cosine theta equals 3 over 5 and theta is in the fourth quadrant. The question is to find the values of all the trigonometry functions at theta. Since theta is in the fourth quadrant, sine theta equals negative square root of 1 minus cosine squared theta, which equals negative 4 over 5. Accordingly, tangent theta equals the ratio of sine theta to cosine theta, which equals negative 4 over 3. Hence, cotangent theta equals 1 over tangent theta, which equals negative 3 over 4. Secant theta equals 1 over cosine theta, which equals 5 over 3. And finally, cosecant theta equals 5 over 4. In example 3, A, B, and C are the three inner angles of a triangle in radians. The question is to determine whether the following four statements are correct. As for the first statement, since sine A plus B equals sine pi minus C, which equals sine C, so the first statement is correct. We apply the complement rule to the left-hand side of the second statement and find sine A plus B equals sine C, which is not equal to negative cosine C. So the second statement is incorrect. As for the next statement, since sine pi minus A all over 4 equals cosine pi over 2 minus pi minus A all over 4, which equals cosine pi plus A all over 4. So it is correct. As for the last statement, since tangent A plus B all over 2 equals tangent pi over 2 minus C over 2, which equals cotangent C over 2. So the last statement is correct. In summary, statements 1, 3, and 4 are correct. Example 4 is to evaluate the expression of sine, cosine, and tangent modulus functions over their corresponding functions. And the question is to find the set containing all the possible values of fx based on the given function rule. According to the given criterion, we need to discuss the function value in each quadrant. Hence, when x is in the first quadrant, y equals 3. When x is in the second quadrant, y equals negative 1. When x is in the third quadrant, y equals negative 1. When x is in the fourth quadrant, y equals negative 1. Therefore, the set has two members, negative 1 and 3. So the correct answer is C. Example 5 is a similar type of question of the previous example. Based on the given rule, of the trigonometry expression, we need to discuss the outcome of the expression in every quadrant. So when theta is in the first quadrant, the trigonometry expression equals 4. When theta is in the second quadrant, the expression equals -2. When theta is in the third quadrant, the expression equals 0. When theta is in the fourth quadrant, the expression equals -2. So the possible outcome of the trigonometry expressions are -2, 0, and 4. Example 6 is to prove the two trigonometry relations. As for the first relation, the left-hand side of the statement equals 1 minus sine squared theta, or in parentheses times cosine theta, then times the ratio of sine theta to cosine theta, which can be further simplified to 1 minus sine squared theta, or in parentheses times sine theta. After being expanded, it equals sine theta minus sine cubed theta, which equals the expression of the right-hand side of the statement. As for the second relation, we expand the two complete squares on the left-hand side of the statement, and then we find both of the middle terms of the complete square are cancelled each other. So it equals 25 sine squared theta plus 25 cosine squared theta, which equals 25 as required. Example 7 is to simplify 4 trigonometry expressions. As for the first one, the expression equals the ratio of 6 sine squared theta to 2 sine theta, which equals 3 sine theta. As for the second expression, we take the common factor sine theta from the numerator, and it becomes sine theta times sine squared theta plus cosine squared theta, or in parentheses, which equals sine theta. So the second expression equals sine theta over cosine theta, which is tangent theta. As for the next expression, since tangent squared theta minus secant squared theta equals -1, the third expression equals -1 over cosecant theta, which equals negative sine theta. After taking out the common factor cosine squared theta from the numerator, the last expression equals 7 times cosine squared theta over sine squared theta, which equals 7 cotangent squared theta. Example 8 is to evaluate a trigonometry expression. The first step is to transfer and find these angles equivalent to the first quadrant angles. So the expression equals negative tangent pi over 6 plus cotangent pi over 3 plus sine squared pi over 4. Due to complementary relation between tangent and cotangent functions, the expression equals sine squared pi over 4, which is 1 over 2. Example 9 is to simplify two trigonometry expressions, given that theta is between 0 and pi over 2. As for the first expression, it is simplified using the supplementary relation to the ratio of negative sine theta to cosine theta, which is negative tangent theta. As for the second expression, it is simplified using both complementary and supplementary relations. So the expression is simplified to cosine theta times sine theta over negative cosine theta, which equals negative sine theta. Example 10 is to evaluate sine theta plus cosine theta, given that theta is an inner angle of a triangle and sine 2 theta equals 2 over 3. According to the given criteria, we square the expression of sine theta plus cosine theta, and then it becomes 1 plus 2 sine theta cosine theta, which equals 1 plus sine 2 theta. So sine theta plus cosine theta, or in parentheses squared, equals 1 plus 2 over 3, which is 5 over 3. Since theta is an inner angle of a triangle, and sine 2 theta equals 2 over 3, which is greater than 0, obviously cosine theta here is greater than 0. Therefore, sine theta plus cosine theta equals square root 15 all over 3. Example 11 is to evaluate a trigonometry expression of 3 cosine squared theta plus cosine the fourth theta minus 2 sine theta plus 1, given that sine theta plus sine squared theta equals 1. Since sine theta plus sine squared theta equals 1, sine theta equals 1 minus sine squared theta, which equals cosine squared theta. So the expression equals 3 sine theta plus sine squared theta minus 2 sine theta plus 1, which equals sine squared theta plus sine theta plus 1. We know from the above given criteria that it equals 1 plus 1, which equals 2. Example 12 is to prove the relation that arctangent 1 over 2 plus arctangent 1 over 3 equals pi over 4. We start by taking a tangent function on the left hand side of the equation and then apply the tangent addition rule. Hence the tangent function of the left hand side equals 1 over 2 plus 1 over 3, or over the result of 1 minus 1 over 2 times 1 over 3, which equals 1. Since tangent pi over 4 equals 1, then the relation is proved as required. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.